Hello everyone! Welcome to our CATIA Systems Talk session. My name is Gitana Strazdauske and our topic today is Modeling of Green Hydrogen, Production and Treatment. The topic will be presented by two multi-physics modeling software engineering managers, Maren Ditze and Imke Lisa Kruger. During the session, they will detailize the principle of modeling green hydrogen production and treatment using Dymola and its specialized Modelica library. They will show you the tools to design and optimize green hydrogen production processes and contribute to a sustainable energy future. As always, during and after the presentation, you will be able to ask questions in the QA section. I wish everyone a good learning time. And now, Imke and Maren, the stage is yours.
Yes, thank you, Gitana. And hello, welcome everyone from my side to our presentation today about modeling of green hydrogen production and treatment. First, I want to introduce us to you, the speakers. My colleague Imke, who's been modeling and developing with Dymola and Modelica for over 15 years now, and focusing on the topics of thermal management, batteries, and hydrogen systems. And then myself, I've been also working and developing in Dymola and Modelica for more than 10 years, and my background is on thermodynamics and chemical engineering. I'd like to give you a short overview about what we talk today. We will start with green hydrogen with a small background. Then we will introduce system simulation with Dymola to you. This is the tool we use where we develop and where we model. And then we will show you some models, some examples, and give you some simulation results, first in hydrogen production and then in hydrogen purification. What is green hydrogen? Green hydrogen is hydrogen that is produced by renewable energies. I'm sorry. Yeah. Why do we need it? We need it, of course, to slow down the climate change. Then we can use it as a storage of energy. We can use it, for example, for decentralized power supply on islands, and, for example, for the decarbonization of steel production. Why do we simulate at all? For the productions, there are some challenges. For example, we have a high fluctuation of the energy supply because we use renewable energies. Then there are large storage volumes due to the low density of hydrogen. And we have a high energy consumption with a potential to optimization and reduction. On the purification side, we can, for example, compare or set up or test different simulation approaches, different systems. We can optimize the purity, the energy consumption, and we can develop control strategies. And now I hand over to my colleague Imke.
Yes, so thank you, Maren, for this introduction. Before we start and present what we have done and present our work, I would like to give you a short introduction to system simulation, because mostly on CATIA Systems TV talk, we were dealing with systems engineering. And so a system simulation is defined that we have a mathematical representation of a system to predict the behavior in different conditions. And typically we have equations, algorithm, or data that describe the interactions between the components of a system, but also the behavior of the component themselves. And system simulation focuses on the essential components and their interactions. So we leave out not so important components in order to have faster simulations. We can identify critical parameters and also their impact on the system's behavior, so that we know which parameters are worth studying and higher detailed level. And system simulation facilitates the collaboration between experts from different disciplines. What we can also see for here in this example, because I'm more from the thermodynamic part, and Maren, she's focusing on the chemical engineering part of hydrogen systems. So I would like now to introduce you to the framework that we're using. So at the core is the Modelica language. Modelica is a modeling language. It's just open source and can be used for multi-physics simulation models. With the language Modelica, Maren and I, we built our Modelica libraries. In my case, it's the hydrogen library. Maren is responsible for the process modeling and engineering library. We write components in Modelica language, and they are then structured into packages that contain different components in order to model systems, what you want to model. In order to be able to simulate then the models that you build of the system, you need a simulation environment. You can use, for example, Dymola for this. That's an environment where you can also write your own components and implement further libraries. But you can also use the system simulation apps. That's a relatively new possibility. It enables people that don't know Modelica, but they can still use then components from our libraries and do simulation studies, for example. And I will show this in my slides later on. So now we would like to share and show our research and our development efforts. And I will start with a short introduction to the Hydrogen Library. That's the project I'm working on. So the Hydrogen Library is a Modelica library that focuses on models with a rather low complexity. So, that we have for fast simulations, and also, which is quite important, I think, is that you have a rather simple parameterization, because often you lack the parameters for complex models, and I focused on parameters that are available as data sheets from the manufacturer. With the hydrogen library, you can model complete hydrogen systems. For example, for production, we have electrolyzers, or also a reformation modeling. For example, here at the bottom, this is a methane reformation system. But we also have models for storage or for fuel cells. With Dymola, you can also get demo models for drones, and also a complete hydrogen-powered bus in your Dymola software. So this is now the model that I use for the studies. Change. So we have here wind turbines. It's now here a mixture of on and offshore. I use data from the real German wind power production and scaled it to a maximum power of 3 megawatts. Then we have here a battery. It can be used as a buffer. So if the wind energy is too high, excess energy for the electrolyzer, the energy can be stored in the battery. And if the wind is not blowing, for example, which can happen from time to time, then we can use the energy stored in the battery to support the supply of the electrolyzers. Energy that cannot be used by the electrolyzers or the battery, because the battery is full and we are already at maximum power for the electrolyzers, are going to the grid. And what we can find out with this model is we can calculate what the maximum production of hydrogen, so how much hydrogen can I produce, how can we minimize the excess energy, and also we would like to find the ideal number of electrolyzers for our system. So we're now taking a closer look at the electrolyzer model. This actually is the component from the hydrogen library. It's a proton exchange membrane electrolyzer. It produces oxygen and hydrogen on the electrodes. It's a semi-empiric model, so we need some measurements in order to parameterize it. It has a temperature dependency. We are considering pump losses, because for electrolyzer, you need to pump water to the electrodes. And what is quite important is that we cannot exceed a maximum slew rate, so we cannot ramp up the power too fast, because this is not possible, or it's damaging the electrolyzers. And at the bottom here on the right, you can see a typical curve for the efficiency of an electrolyzer, and you can see that the maximum efficiency is reached at maybe about 50% of the maximum power. So it seems to be favorable to run an electrolyzer not at the maximum available power, but at a lower power. So I wanted to switch to the next slide, but actually, yeah, no. Okay. And I've here prepared a short video that I want to run. It's about a parameter study for a year simulation. So we are simulating a whole year, and we want to vary the number of electrolyzers. Now start the video. And we choose here a parameter study. So we choose the parameter that we want to vary. This is the number of parameters. We choose different values and the number of points we want to simulate. Then at the bottom of the user interface, I chose 3 different output variables: the energy that is consumed by the electrolyzer, the amount of hydrogen that is produced, and as a third variable, I chose the amount of energy that is going to the grid, the excess energy. And now, these 5 simulations are calculated in parallel, and then we can see here the plot of the results. Here on the top left, we have the energy that is consumed by the electrolyzer, and we can see that as for the total mass of hydrogen, the more electrolyzers we use, the more energy is consumed by the electrolyzer. And we can see on the bottom that the energy to the grid is reduced if we use more electrolyzers in this case. And here I've noted the end results. So we can see that the more electrolyzers we use, we get more hydrogen per year. But we can also see that the difference between the 20 electrolyzers and 25 electrolyzers is way higher than the difference between 35 and 40 electrolyzers. So we have to study maybe a bit closer, which could be the optimal number of electrolyzers. And for the amount of energy that is needed to produce 1 kilogram of hydrogen, we can now here see the result of what I've shown you before, that the more electrolyzers we have, the less energy is needed per kilogram hydrogen, because we can run the electrolyzers at a lower power rate. And I've now simulated here for, as an example, for 30 electrolyzers for a shorter time period to make it a little bit more obvious, the electric power over time. You can see in purple is the power consumed by the electrolyzer. Blue is the wind power, and in orange you can see the power that is going inside or coming from the battery. So at the beginning here we have electrolyzer and wind power running in parallel. Here we can see that the wind power is exceeding the maximum power that can be consumed by the electrolyzer, and the excess power is then can go into the battery just as the battery is full, which is here in this case. So here's the battery full, so no more energy can be charged into the battery and has to go to the grid. Then the wind is becoming slower, so we have energy or less power from the wind, and we can now support the electrolyzers with the power stored in the battery just until the battery is empty. So what we can see here, what could also be another interesting part to study would be the capacity of the battery. There's of course also variable, but that's another topic. And after we have now taken a short look at the hydrogen production, I would now hand over to Maren, because she's showing what you have to do now with the hydrogen, because you cannot use it as it is coming from the electrolyzer. And yeah, now Maren, the floor is yours.
Thank you very much, Imke, for this interesting insight into hydrogen production. Yeah, and I will now tell you a bit about purification of hydrogen and show you the library I've developed for this purpose or for general separation purposes. The library is called Process Modeling and Engineering Library, and it is mainly about thermal separation processes like distillation in multi-phase, multi-component mixtures. For this purpose, we use the external fluid data multiflash, and we developed interface to let Dymola communicate with multiflash. At the right, you see some examples of modeling of distillation systems or thermal separation systems. If we have a closer look at one of them, we can see there's a distillation column in the middle here, which is the heart of this system, but also in general of the library. But we do also have other components like tanks, pumps, or valves in order to simulate this whole system. Then I will give you a quick overview about distillation. You might have heard of it. Some might be pros in it or know it very well. Some maybe didn't hear too much about it, but you all might have seen these towers somewhere. The question is what happens inside. Here we have a drawing of a distillation column, and we see that we have a product mixture, so a mixture of components that goes in here. It separates into liquid that goes down and gas that goes up, and we can take out this gas product and we can take a part of it and bring it back into the column. We can do the same at the bottom, so we evaporate a part of the product and bring it back into the column. Then we have a counter flow system inside. We have a gas flow going up, and a liquid flow going down. And as you see, we have different stages here. But what happens on these stages? We have on each stage a specific thermodynamic equilibrium. This means we have at each stage a different pressure and temperature. And in this equilibrium, the fluid turns into one liquid and one vapor phase. And the point about distillation is that the component concentration in both of the phases are different. So we have a separation in this equilibrium. And if we do this again and again, what we do in a distillation column, because we have many stages, we will have a very pure separation of the components. Now I want to give you two examples of thermal separation concerning hydrogen. The first approach I want to present to you is hydrogen total purification with a cryogenic distillation. This can be used, for example, if you have if there's hydrogen from green energy production. It has impurities like water, but also nitrogen or oxygen, and all of this can be reduced by this process. And then I have another approach I want to share with you. It's the hydrogen drying by absorption. And in this case, this can be used if the main impurity in the hydrogen is water, or if you want to combine it with other purification systems. I want to start with the cryogenic distillation. At the left, we have a mixture of hydrogen with impurities, water, nitrogen, and oxygen. Then in cryogenic distillation, we have to go down to very low temperatures because the gas has to be liquefied, and this happens at below minus 240 degrees. So if we go down to this low temperature, the water will simply freeze out and we can remove it from the gas. The dry gas goes into the column, and we see that hydrogen will come out as a head product and nitrogen and oxygen will be the bottom product. Let's have a look at the results. But first, some more info. So we, as I said, we are very low in temperature. We are at below minus 240 degrees. And in this system, we have 3 trays. So this is the mixture that goes in. All the percentage you see is in mole fraction. So we have 7 mole% of impurities in the hydrogen. And if we have a look at the simulation results, here this simulation shows that we get almost 100% of hydrogen with a very low amount of impurities. And at the bottom, we get mainly oxygen and nitrogen with a little bit of hydrogen. Then we come to the next system, the absorption system, which is a bit more complex because we have 2 columns. The left column is the absorption column itself, and the right column is the regeneration system for the glycol. So at the left, we have the same mixture here going in. It's the same hydrogen with impurities. Then we raise the pressure. So during this compression, some part of the water will already be liquefied and we can take it out. The rest, still wet gas, goes into the column. At the top, we add 3-ethylene glycol. This glycol drops through the column and absorbs the water vapor. And what comes out is dry gas. And at the bottom, we have a mixture of glycol and water. This glycol-water mixture goes into the next column, and there is a simple distillation that separates these 2 components, water and glycol. At the left column, at the absorption column, we have 10 trays and quite high pressure, about over 70 bars. And at the right side, we have quite high temperature. We go up to 265 degrees, but we have only 3 trays and moderate pressure. If we look at the left system, we see we have pure glycol going in and the same mixture we saw before. And what comes out is dry gas. So we see that what we removed from this gas is only the water, and we have a very low water amount here. And at the bottom, we have a mixture of water and 3-ethylene glycol, still with some small impurities. We take this bottom product and we put it into the next column. So this is this goes into the next column. This is the feed. And then we have a look at the results as well. We see that the head product is mainly water, still with some impurities because we had some impurities that went into the system. And on top, we have a high amount of glycol. So what we can show here is that both of these approaches work quite well. But still here, for example, we see there are some impurities. And for example, if we want to improve the amount of water in the subproduct, we want to reduce it, then we could, for example, change the backflow of the products or the backflow ratio, or we could also raise the number of trays, but we can also change other parameters like pressure, temperature, or also other dimensioning of the column. And now we are already at the end of our presentation. So what you learned today is that the hydrogen library helps you to study big systems for hydrogen production, from source to end user, and to identify component interactions. Then we could show you that a year simulation is very good to evaluate basic parameters of hydrogen production, for example, the sizing of electrolyzers. And we showed that the variable efficiency of the electrolyzers has a high impact on the energy that is used, that is consumed, or that is needed for 1 kilogram of hydrogen produced. For the purification, we showed you the process modeling and engineering library, and we showed that it can be used for different thermal separation approaches for purification or drying of hydrogen. And we could show that a high hydrogen purity can be reached by cryogenic distillation with very low impurities, and the absorption system is very suitable for producing very dry gases with a very low water content. Yeah, thank you for listening, and now we are open for questions.
Many thanks, Marian and Imke. That was really incredible to watch and to listen to your talk. So I see that there is some comments that it was very useful information. Also, the other comment is that this is exactly what the user was looking for. I do not see the questions, but I have a few questions up front. So, and one is where do I need to start? How to start doing what you showed, and what do I need to model the hydrogen system?
Yeah, maybe I can start. So the first thing would be that you need a Dymola, so a simulation environment, and maybe some Modelica knowledge could be helpful as well. Then you would need, depending on if you want to model the hydrogen production or the treatment, you need a license for one of our libraries. Then most of the components that you will need are already inside the library. So you will just have, you need an idea what you want to model, and then you can just arrange your system and connect the components and start to simulate.
Okay, and who are the users, the customers? In which industry they are working?
So yeah, so maybe I start with the for my library, for the PME library. So there it's different areas. So all areas where thermal separation is needed. This is, for example, in the gas and oil industry, very common. Or also now coming more and more the CO2 absorption systems, CO2 storage systems, where CO2 is separated, for example, from seawater or from the air and then captured.
Okay, so this is quite useful in the areas where there is no fresh water. So this system could be used.
No, yeah, it can actually be used for this case as well, but it's more for carbon capture, just to reduce the carbon from the atmosphere and store it somewhere, and reduce the carbon footprint.
Oh, we have one question from the user, from the audience. Could we couple the hydrogen production with the hydrogen purification systems and simulate them together?
I think that's a question for Maren. I guess it would work, but we haven't tried it so far because I have a very dynamic system, and Maren's, I think she used steady inputs. But Maren, maybe you would like to comment on that?
Yeah, so far it is what Imke said, that the level of detail is a bit different, because the focus on Imke's system, on the production system, is more on year simulations on very big systems, but not that detailed. And I have more the approach to be more detailed. but not to have, I haven't done year simulations yet. So this could be a challenge, but in general, it should be possible to, to simulate the systems together.
Okay, so thank you everyone for being together this half an hour. So we really learned something. Thank you, Maren, Imke, and thanks everyone who watched us. And if you have some questions, if you want to ask the speakers, I really encourage you to visit the community go.3ds.com/cyber.systems, and you will find the post of this CATIA systems talk, and you can ask questions. And usually we are very happy to see questions, and we are answering them. So let's build a community together. So thanks a lot for everyone, and see you next month. Bye.
Bye.
Bye.